And this relies on the fact that when we talk about enthalpy, or we talk about the heat change of a reaction, this is a state function. And anytime we're talking about a state function, it's independent of path. So essentially, all that we're worried about is the state that we started in. So for example, when we were talking about the oxidation of glucose, the state that we start in are the reactants, so it's glucose plus oxygen, and what we ended up with were 6 moles each of carbon dioxide and water. So we don't care how we get there in terms of making this calculation. All we're interested in is the difference between those two states to think about the overall change in enthalpy. So for example, when we talked about how we could calculate this, one way that we can do it, and we'll look at these numbers even more specifically in a second, is thinking about, instead of going straight down here, which we might not have the numbers available to us to calculate directly, we can think about, well, what happens if instead we break apart this glucose molecule and decompose it into its elements, because using tables in the back of our book, for example, we can figure out what the change in enthalpy is of this reaction here. That doesn't quite get us to where we need to go, though, so then we can think about the enthalpy of formation of 6 carbon dioxide molecules, and then we can go one step further and think about the enthalpy of formation for 6 water molecules. So this is just a roundabout way of going from here to here. Instead, we went up and then down, but because it's a state function, we're absolutely allowed to do this.